Hi there, faithful math followers. Welcome to lesson 20-2 that is, starting up on page 347 in your book. So on page 347, we're going to start learning about exponential growth, which we've taken a peek at before. But we're going to be able to determine the growth factor of an exponential function, which if you remember back to an EA you took, you have a little experience with. You're also going to graph and analyze those exponential growth functions and identify and write exponential growth functions from a story. So let's get cracking. Does this slide background remind you of an Old West saloon? That's what it reminds me of. Velvet wallpaper. Anyway, I digress. So let's see here. The National Association of Realtors estimates that on average, the price of a house doubles every 10 years. Tony's grandparents bought a house in 1960 for $10,000. Wow, can you imagine? Assume that the trend identified by the National Association of Realtors applies to Tony's grandparents' house. So what was the value of their house in 1970 and in 1980? So they bought it in 1960, and they say that the price doubles every 10 years. So in 1970, it would be worth $20,000. And in 1980, it would be worth $40,000. Compute the difference in value from 1960 to 1970. So it changed by 10,000. Went from 10 to 20. And then compute the ratio of 1970 to the 1960 value. So just a little reminder, the ratio of A to B is evaluated by dividing A by B. So the ratio of A to B would be A over B. So 1970 to 1960 would be 20,000 over 10,000, which would equal 2. So then we need to complete a table of values here from 1960 to 2010. So the decade since 1960 started out as 1960, so 0 since then. Then it was 1 decade since then, and now it's worth 20,000. The difference between consecutive decades is 10,000, and the ratio of consecutive decades, 20,000 to 10,000, is 2. And then 2 decades after 1960, it's worth 40,000 in 1980. And the difference between consecutive years is 20,000 from 20 to 40 this time. And the ratio is still, if you do 40,000 divided by 20,000 for consecutive decades, it's still 2. In 1990s, 3 decades since 1960. Now it's going to be worth 80,000 if it doubles again. And so consecutive decades would give you a $40,000 difference, but it would still be a common ratio of 2 if I did 80 divided by 40,000. Now, 4 decades later, it's going to be worth 160,000. This sounds more like it, doesn't it? And the difference between these two is 80,000, but the ratio is still 2. And then 1 decade after that, so 5 decades since 1960, now it's going to be worth 320,000. And the difference there is 160,000 between this one and this one. And then the ratio, though, still 160 divided by 80 would still be 2. So what patterns do you notice in the table? Well, we notice that the difference in values from 1 decade to the next are not the same. They're different, but they always do increase every time. And then the ratios of consecutive decades are constant. They're always the same. They're always 2. So then they want us to write the house values as a sequence. Identify the sequence as arithmetic or geometric. So let's see. So it would be the house values. So 10,000. I'm just going to write 10K, 20K, 40K, 80K. You can write out thousands if you want. 160K, 320K. And it's not changing by a constant rate, is it? But it does have a constant ratio, common ratio. So this is geometric. It's a geometric sequence. And the justification is it changes by a common ratio, meaning every time it's multiplied by the same amount. And that's what we learned in the last section. So now we're going to put that on a graph. So these are the decades since 1960. So 1, 2, 3, 4. So in the first decade, which would be 1970, it was worth 20,000. So that'll be right there. In the second decade, it was worth 40. And in the third decade, it was worth 80. And in the fifth decade, it was, fourth decade, it was worth 160. And in the fifth decade, it was worth 320. So 320. So the data comparing the number of decades since 1960 and the value of the house are not linear. And we're going to use the table and the graph to explain why. Well, the table shows the rate of change is different. So it is not constant. In order to be linear, it would have to have a constant rate of change. And the graph does not show a line. It better not show a line. If it does show a line, that means that the rate of change was constant. So these two, table and graph, wouldn't match. So using the information we have regarding the house value, predict the value of the house in the year 2020. Explain how you made your prediction. So we already know it's worth 160 in 2010. So one decade later, no wait, we know it's worth 320,000 in 2010. So one decade later, that's going to double again. So it's going to be 640,000. One more decade from 2010 to explain my reasoning. So double that value. We doubled the 2010 value. Tony would like to know what the value of the house was in 2005. Using the same data, predict the house value in 2005. Explain how you made your prediction. Well, we know that in 2000 it was worth 160,000, and in 2010 it was worth 320,000. 2005 would be halfway between those. So if we this changed by 80, so if we go halfway, maybe we would add 40 to it. Does that make sense? So it'd be roughly 200. What am I talking about? It didn't. Oh, sorry. I was looking. Yeah, it didn't go up 80. It went up 160,000 right here. That's what it went up right there. It went up 160,000 from this year to this year. So it went up 160,000. So halfway, I apologize. I'm a little bit tired here. So halfway, 2005, halfway of 160,000 would be going up 80,000. I could tell that wasn't going to be halfway, and I was trying to think of what I did. So 80,000 more would put us at 240,000. So if I took my 160 where I was in 2000 and then In 2010, it was worth 320,000. So halfway in between there, in 2005, it would be worth 240,000. Halfway in between, so 80,000 higher. Explain, so we went halfway between the 2000 and 2010 values. Sorry about that. So now we're going to understand some of the parts of the equation and what the pieces mean. So the increase in house value for Tony's grandparents' house is an example of exponential growth. Exponential growth can be modeled using an exponential function. As long as b is greater than 1, okay, so b has to be bigger than 1, the function f of x equals a times b to the x power, here's your function for exponential growth, models exponential growth. The value b is the growth factor. And you'll remember that it's like a common ratio. It's the 1 to the power, so it's the factor that's getting multiplied over and over and over every year or every time period. So that's the growth factor of the exponential function. So the function that can be used to model the house value is h of t, in other words, house based on time, house value based on time, is 10,000, that's the starting amount, times 2 to the power of t. T being standing in for x because we're talking about time here. So the growth factor is always the base of the power, so the growth factor in this function is 2. So now we want to talk about the ever-present domain and range. So we've got to identify the meaning of h of t, that's the house value, so that's going to be our range, that's the output, and of t, which is the years since 1960. And so the reasonable domain and range are pretty much anything that's not a negative number. So that house value could go all the way down to 0. So the range would be any number greater than or equal to 0, because it could be any part of a dollar amount. And the years since 1960 would be the same. So the domain, it could be all the way back to 1960, which would be 0 years since then. So t would be greater than or equal to 0 also. So anything that's 0 or more would work for the domain and the range in this situation. And now we're going to explain in our own words why the growth factor must be greater than 1. So since it says in your own words, perhaps you should give it a try. Pause me until you've tried it and then listen to what I have to say. So we've sort of talked about this before. If it's a growth factor, in order for something to grow, you have to multiply by a number bigger than 1. So multiplying by a number less than 1 will make values shrink. And then if you multiply by 1 itself, it'll not change anything. So 1 itself will not change the value. So in order for it to grow, that growth factor has to be something greater than 1 or nothing's going to get bigger. All right, so we're going to complete this table of values and then graph it. So when t was 1, I guess, let's say, then this would be 20,000. And when t was 2, 40,000. Can you picture that? I'm plugging it in here. So if t was 3, 2 to the third is 8. And 8 times 10,000 would be 80,000. 2 to the fourth power would be 16. And 16 times 10,000 would be 160,000. And 2 to the fifth power is 32 times 10,000 would be 320,000. So we're going to graph it. So at 1 decade, it was 1 to the, I can't quite figure out why they chose this for the scale for the outputs, but 10 to the 5th power is 100,000. So this is 100,000, this is 200,000, 300,000, 400,000. Just a little bit of strange choice there, but so 1 decade would be, let's see, if this is 100, this must be 50, so it'll be about here, and then 40,000, and then the 3rd decade would be 80,000, and the 4th decade would be 160,000, and the 5th decade would be 320,000. So it would be looking kind of like this, because there's lots of years in between there too. So what is the value of the house in 1960? That was 10,000. Describe how this value is related to the function. So it's the value when t equals 0. So 2 to the 0 power equals 1. So in 0 decades since 1960, it was worth 10,000. And the graph, on the graph, it is the y-intercept. Because it's when the decades was 0, the value was 10,000. The starting value of the exponential function. All right, now they throw us a couple twists here. So these are interesting questions because of the way they want us to write it, but let's not panic about it if it feels a little confusing. So let's suppose the growth factor were doubled. That's no big deal. If the old growth factor was 2, then this growth factor is going to be 4. So the trick is they want us to rewrite the function with the base of the exponential term still equal to 2. Well, we were just about to change it to 4. So let's see what else we could do. So h of t equals 10,000 times 4 to the t is what we're after. Well, we know that they're going to give us a tip here. We know that 2 squared equals 4. So this 4 could look like this. We could say, all right, well, let's call that 10,000 times 2 squared to the t power. Well, then we can, there's exponent rules that says a power of a power means that you multiply the powers. So here's the way this would come out. It would look like h of t equals 10,000 times 2 to the 2t. So instead of just the power of t, it would be the power of double the time. And that's rare that we need to do that, but they just wanted to show us how to use the exponent rules to look at this in 2 different forms. This way with the growth rate just doubled, and this way keeping the growth rate at the base of 2. So now if we use our function, this new function, this one, which is the same as this one, explain how the range compares to the original function. Well, for t equals 0, so at 0 time, the range would still be 10,000. So that won't change anything. So it's still going to start at 10,000 because you're still going to have 0 power of 2, which is just gives you 1. So then what's going to happen though, for anything t greater than 0, the range value, the new range value, right? The range value of the new function will equal the old range value at double the years. Does that make sense to you? So like the new range value at 1 year is going to equal the old range value of 2 years. And the new range value of 2 years is going to equal the old range value of 4 years. At 2 times the years. So the new function is going to, when you plug in a t value, the range is going to come out equaling what the range would have been at 2 times the t value on the old function. So we can talk about that if you have questions.